Hello, my name is Cotto, and one of my greatest interests is in renewable energy. For my material science project, I'm going to be giving you a small overview of photovoltaics. Starting off, what are photovoltaics? Photovoltaics, which I may call PVs at this presentation, are the electronics responsible for the function of solar panels, devices that harvest solar radiation as a renewable energy source. We name them after the photovoltaic effect, which is the process they use to create electrical charge. In their hierarchy, PVs are the core components of solar cells, which are combined into modules in the larger solar systems. So let's take a look at what PVs are made of. All photovoltaics start off as semiconductors, which are defined by having electrical conductivity between that of insulators and conductors. This key property makes it so that every electronic we use is actually made of semiconductors. Because the conductivity sits on the fence, we can actually adjust it to be more insulating or conductive with specifically placed impurities in a process we call doping. A few examples of semiconductors are silicon, the most commonly used semiconductor, gallium arsenide, the one we'll talk about later, and germanium, the first semiconductor to be discovered and used. If you can notice, all of these semiconductors are crystals. It's a fact that most semiconductors are solid-state crystals, especially of group 4, and the more monocrystalline the material, the better they usually perform. The next thing we need to talk about is the band gap, which is what determines how much energy the photovoltaic effect produces. Every atom has a valence shell, with its outermost electron sitting at the lowest energy state. However, above the valence band is a higher energy level we call the conduction band. If an electron is excited to this state, they break free of the valence band, but this movement takes a discrete amount of energy. What we call the photovoltaic effect is when a photon smacks into an atom and the energy it carried excites the valence electrons. If a photon has less energy than is required for the electron to move, it passes through the solar cell and nothing happens. But if the photon has enough energy, the electron takes the exact amount of electron volts and jumps from the valence to the conduction band. This amount of energy is called the band gap. But there is a catch. The photovoltaic effect can only give off the same amount of energy the electron needed to move. Even if a large solar flare level photon approaches your photovoltaic cell, the electrical output from each photovoltaic effect remains the same, and the rest of the energy gets wasted. Once the photovoltaic effect energizes an electron, the potential for an electrical charge is carried by two things: the free electron, which now escaped, and the hole that it left behind. Free electrons is self-explanatory, and once they're knocked out of their valence shell, they can move around the material. In doping, they can be sourced from group 5 elements. When group 5 elements bond with 4 neighboring group 4 elements, there's an extra valence electron, which now becomes free. The hole is the now unsatisfied covalent bond that's left behind because one of the two electrons now just left. If you have a group 4 semiconductor like silicon, you can supply holes using group 3 elements in doping, such as gallium or boron. Now, we have a problem with the creation of the hole electron pair, which is how do you prevent recombination, which is when the electron and the hole just come back together and you get no power out of it. And the answer is p-n junctions. P-n junctions are a ubiquitous design you'll find in nearly all photovoltaics. A p-n junction is made of a single semiconductor material with p-type and n-type doping on either ends. The p-type has an abundance of group 3 impurities, which make substitutional defects. Like mentioned before, since group 3 only has 3 valence electrons, when you put it in a group 4 semiconductor, it can only fulfill 3 of 4 bonds, creating an abundance of holes. The n-type is made of group 5 substitutional defects, and since they come with 5 valence electrons, that extra one becomes a free electron that can fly around the material. What the p-n junction does is create these substitutional defects in the crystal structure. Even though the carriers can move around, the ions that they came from can't, which means that when the carriers leave them, the ions' cores get exposed. Since all the positives are on the n side and all the negative ion cores are on the p side, this creates an electrical field moving from right to left. Since electrons move opposite direction of an electrical field and the holes move with it, this reinforces the separation and you create what's called the depletion zone. Any carrier that's caught in the depletion zone will get flung out to one side or the other, usually the side that it belongs to. In doing so, whenever a photovoltaic effect actually creates an electron-hole pair, we can separate them effectively, which gives us the ability to harvest a charge. Quickly talking about some types of photovoltaic cells, we have silicon solar cells, the most common. They come in monocrystalline and polycrystalline varieties, and like mentioned before, the monocrystallines are of a higher efficiency, but come at slightly higher costs. Thin film solar cells are fabricated from extremely small amounts of silicon being deposited onto a substrate. They can be actually flexible because of this. 3 years ago, they were the most expensive, but now after 3 years of research, they are the cheapest, but this comes with lower efficiency and the least durability. High efficiency solar cells not only have the highest light to power ratio, but the most durable. They have longer manufacturing processes, which leads to the highest costs. These are heavily used in space industry where size, weight, and power benefits are prioritized. And some examples are gallium arsenide and multi-junctions, which stack junctions on top of each other. What we're going to be talking about today is, this is a picture of the thin film solar cells. As you can see, flexible. What we're going to be talking about today is gallium arsenide, which is a 3-5 photovoltaic cell, which is highly efficient, lightweight, and resilient to damaged moisture and radiation. Gallium arsenide, since it comes from two different elements, is usually manufactured using these two specialty methods, which is organometallic vapor phase epitaxy and molecular beam epitaxy. MOVPE is a chemical reaction actually that happens at atmospheric pressure, where precursor gases are used to react and create the crystal. Molecular beam epitaxy, on the other hand, is a physical crystallization method. Now moving on, I have an example of a gallium arsenide crystal structure to show you all. So let me pull that out now. So what we have here is the gallium arsenide crystal. In blue, you'll see the gallium 3+, and in green, the arsenic 3-. As you can see, it has a very unique shape. Now, the gallium arsenide crystal has actually two sublattices of face-centered cubic. So it's as if it has two face-centered cubic structures inside of each other, and they're offset by half a diagonal. This type of orientation is called cubic sphalerite, I believe. And this is just, the small dots represent the same atoms but shrunk down to a tenth of their size. And behind it, if I unhide, I have a copy of the same network of chemical bonds. And this is a repeat structure, just the atoms are shrunk down so you can really see how the chemical bonds are. And that should be about all. Let me get rid of some of these dots. And you're left with this structure. And that'll conclude the presentation. Thank you for watching.